Hello everyone and welcome back to a new video in the introduction to the finite element method. And of course, this is the series in which we are talking about the book, A First Course in the Finite Element Method by Dariel L. Logan. And in today's video, we're going to be exploring an example given by the book and drawing some strange conclusions. With that being said, sit back, relax, and enjoy the show. Okay, so for today's video, we have a quick topic we need to cover before we start talking about the example, which is going to be the basis of equivalent nodal forces. Now, the book basically goes on a long mathematical tantrum talking about how you can calculate the equivalent nodal forces and ends in the end by finding the F surface forces to be a double integration along the surface for the shape functions multiplied by the surface traction. That's a long story, and the recommended reading I have for you is section 6.3 in the book, Treatment of Body and Surface Forces. However, for the purposes of this video, we need the following simple understanding. If I have a load, a pressure, notice that the load here is given in terms of pressure, pounds per square inch, or of course the equivalent, SI equivalent of pascals or newtons per meter square. And before we continue, I just want to draw to your attention that this is a pressure, meaning that you have this sort of loading. You are given a pressure acting on the edge of the element. Basically, the book tells you that it's PLT over 2 and PLT over 2. It's basically the total force divided by 2 for each one of those nodes, something that you should be expecting for an uniform linear distribution. If it was a triangle, you would have 2/3 in one node and 1/3 in one node, something that is a little bit similar to what you have studied in statics. Now, what is the total force you're asking? The total force is P, the pressure, multiplied by the area, which is, of course, the length of the area, which is this thing. I will call it L. You could call it H if you want. Multiplied by the thickness of the domain, which is T. So L by T is the area, the surface area, and multiplied by the pressure gives you the total equivalent force. Of course, this needs to be divided by 2 to find the correct nodal forces, and this is what has happened here. Here, in this case, you would have PL over PLT over 2 from the first side, and PLT over 2 from the second, and that's the distribution. I think this is more than enough for our today's example. You can dive deep in section 6.3 if you want, but that's what I need for today. Okay, now for today's example, it might be a very quick example, to be honest, but there are some peculiar conclusions I want to draw at the end of this example. Now, one strange thing the book does before that is it shows you one big equation, matrix K, which tries to give you the local stiffness matrix of the CST element directly. Now, he gives you this, but doesn't use it. He still uses the TABDB approach. I will show you that. We have this rectangle with surface traction forces. How could I solve that? Now, we don't have rectangular elements yet, so we need to deal with this in terms of triangles. And in terms of triangles, we shall do. So we are basically going to replace this swab of thing here by 2 triangles like this. Of course, I discretize it like this. You could say, no, I want my 2 triangles to be like this. Both are options. Both are 2 options that are available for you. And you would think that this discretization and this discretization should not give you any different answers. They should have the same answer. Well, I'll talk about this at the end, but spoiler, no. This will give you a different solution than this discretization, and we will talk about this at the end. So, okay, the book starts by discretizing the structure as we see. Here, you have triangle number 1 and triangle number 2 and the 2 5,000s. Now, how does he get the 5,000? Well, it's 1,000 psi, or pound per square inch. He multiplies it by the area of the surface, which is 1 multiplied by 10. So 1 multiplied by 10 by 1,000 is 10,000. Divided by 2 gives you the 5,000 each. Perfect. He goes on with this and start dealing with his triangles one by one. Now, for the new viewers here, first of all, this is part of a longer series that talks about the introduction to the finite element method, which I will be linking above. And I want to mention that the triangle elements had a longer solution in which I used my shape functions, and this has been done in the previous video. Now, for today's video, because my point is not in the structuring of the stiffness matrix, I will skip over the fluff and tell you that you need to calculate those things because those are part of your B matrix. Because your B matrix has the derivatives of the shape functions staggered, and then, of course, at the end, crossroad. And we've done this last time. The area, of course, here for the triangle is 10 multiplied by 20 over 2. And this time, my teaching assistant did not mess up. You actually wrote it correctly. Thank you very much. And there's nothing to do. This is a pure mathematical thing. You have to find the B matrix, you have to find the D matrix, and then define or find T multiplied by A multiplied by B transpose dB. Derivation of this has also been discussed before, and I will link some videos in top right so that you can check out those when you have time. So you have your B matrix, you have your D matrix. Now it's mathematical solutions. You could open MATLAB if you want. I will just spare you the details here. This is the stiffness matrix of the first element, and once again, this might be out of character of the CEE channel to just throw out the stiffness matrix like this, but I just want to tell you that I think this is maybe the 4th or 5th video in the triangle series, and maybe the 17th video or the 16th video in the series in general. So I think that I'm warranted to speed up a little bit for the sake of saving time. You can see, of course, K1 being constructed, where the book is assuming that this is I, this is J, and this is M. It's very important to know what the I was, and what the J was, and what the M was. You can notice that he's using I to be node number 1, J to be node number 3, and M to be node number 2. And you would think, wait a minute, why didn't he use I to be node number 1, J to be node number 2, like why didn't he put a J here, and M to be a node number 3? Now this is a very long story, and I don't want to talk about it this time. I will keep this question tabbed. But the idea, at least that you understand this, the idea is that he wants to define a counterclockwise rotation for ijk or ijm. The reason behind this is because this plane element doesn't have only 2 axes. It actually has 3. It has a local x-axis, it has a local y-axis, and it has a local z-axis perpendicular. This is x, this is y. It has a local z-axis perpendicular to the paper. And when he assumes a counterclockwise rotation, the z-axis is going to be towards you, dear viewer, by using the right-hand rule with x and y. The z is going up. And it's very important to maintain the same z direction as the global axis if you deal with shell elements. So this is a kind of foreshadowing for what is to come. But for now, I only want to say that, hey, he's using this intentionally to try keep a counterclockwise rotation. So he's using BDB and giving you basic the stiffness matrix. That's fantastic. He returns and does the same thing for triangle 2. Once again, I want to just quickly tell you that he's using his IJM nodes to be in a counterclockwise orientation. Now, this is a must. If you're an MSc or PhD student, you would think, well, those are 2 triangles, right? I could go clockwise in both cases. And the answer is yes, you could go clockwise in both cases. You could go anything, but you have to maintain the same direction of rotation. If you choose the nodes to be in a clockwise manner, you have to use everywhere clockwise for the same plate element. If you choose counterclockwise, then you have to choose counterclockwise everywhere for the same plate element. And to just spare you the headache, I highly recommend that you use counterclockwise for defining the rotation of the element. Okay, he has K2. What remains is to add K1 with K2, which he's doing here. He's giving you K1, he's giving you K2, and he's adding them together to get the global matrix. But wait. You would think, wait a minute, how is he adding triangle number 1 with triangle number 2? I think you remember from previous videos, there is something called a transformation matrix. And usually we have done this whenever 2 elements had different orientations, so that we cosine and sine their orientations with respect to the global matrix, to the global local sense. So basically the transformation matrix is a transformation between the local and global axis senses. or vice versa, depending on the transpose or not. So you would think, okay, where is the transformation matrix in all of this? The answer is it's not needed. You see, in the beginning, he's giving you this sneaky, almost hidden global x-axis, and this sneaky, almost hidden y-axis, and our assumption for our displacements were the same as the global axis. Don't believe me? Here is a clarification slide I have for you. The global x was going to the right, and the global y was going up y, and the definition of the degrees of freedom of those triangles were the same. You would think, okay, it seems I never need transformation matrices for that, because whatever the orientation of the triangle, I would always be able to just use it, because the local u is in this direction, the local v is in this direction. You know what? Yes, you are. You can use this without any transformation. You would think, okay, why did you teach us the transformation matrix? I'm glad you asked, dear hypothetical viewer. As a matter of fact, the transformation matrix you have seen is a simplification. The transformation matrix might become necessary if you want to program Strado-like structural analysis softwares, where you have plates in one orientation and plates in another orientation, and a third plate in a different orientation. You see, if you have plates in different orientations, you might need to discretize different triangles. Like you might need to do this discretization here, and this discretization here, and this discretization here. Now here, the local u is going to be in this direction, and the local v is going to be in this direction, which corresponds not with the global axis. I mean, look at this. This is inclined with inclined. So in that case, you would need the transformation matrix. In our case, we don't. And I don't think I see the book showing you the transformation matrix ever again in this chapter. It just mentions it and just then seems to be forgetting it. But I just wanted to draw your attention to this. We don't need the transformation matrix, or the transformation matrix for the mathematics nerds is a identity matrix. So we expand, because we will try to add, we're expanding our stiffness matrix by adding zeros. That's not important, because you could just add them together like we did selectively. You add them together and you get your global stiffness matrix. There is nothing else I want to say for now. You have stiffness 1, you have stiffness 2, you add them together to get the global stiffness matrix. You put the forces, you find your boundary conditions, because let me remind you, you have a load in x at 3, load in x at 4, you have a restraint at 2 in both directions, and a restraint at 1 in both directions. Translating this, here you get a restraint in node number 1, a restraint in node number 2, unknown forces, which are your reactions at node number 1 and 2, as well as the applied force x only in node number 3 and x only in node number 4, which can be basically slashed, because remember, if you have zeros, you start slashing and dashing those rows and those columns. Which remains is this block with the forces, and that's what you see here, which solves like this. And here I want to talk about something. First of all, the reactions were never evaluated in this problem, so I ask you to evaluate the reactions. Because you have the displacements, you can use them to evaluate the reactions. And you will notice something very strange when you evaluate the reactions, but I don't want to spoil it for you. If you evaluate reactions and notice something strange, then listen to what I have to talk about here, and then everything should be making sense. So let's talk about some strange things. First of all, he tries to find the stresses of element 1 and 2. This can be done, like in the previous video, by finding sigma, which is the material matrix multiplied by the strain matrix, which is the B matrix, by the displacement matrix U. Yeah, I have done an example in the previous video, so check out that before you continue. He is finding the stress of element number 1 and finding the stress element number 2. Now, I've talked a little bit about this when I went on a side issue for MSc and PhD students, and I think it's time here to address it very quickly for all levels. You see, the book further goes one step further and tries to find the principal stresses of element number 1 and principal stresses of element number 2. This is fine. The issue I have is that you have different stresses for different elements. You would think, okay, this is strange. What's the problem here? The problem is that the force applied is the same, but the location of the force was different. Okay, what else? What else is that you see this line? This boundary line basically separates element number 1 with element number 2. The crazy part is there is no stress continuation. There is a stress discontinuation between element number 1 and 2. You see, at element number 1, if you take this point, this little point that I'm circling here, this little circle, it has those stresses. If you take the point just beside it, the rectangle point, it has different stresses. Now this should not be, but in fact it is, and this is one of the weak points of the finite element method. You will always have those stress discontinuations, but you can mitigate this by, for example, discretizing into more triangles. This would cause lesser and lesser stress discontinuity between elements. Secondly, it has stress discontinuity, and you could use higher order elements. This is something that we'll discuss in the future of this video series. But for now, I just want to draw your attention that, hey, there is a stress discrepancy. Like you see this laser pointer, as long as the laser pointer is pointing inside this triangle, sigma x is 1005. I mean, even look at sigma y. Sigma y is off the charts. Like sigma x and sigma x, you can see some sort of, okay, similarity, but look at sigma y. Sigma y is 300 tension, and now it's negative 1.2 compression. It's like here here the fibers in y are under tension, and suddenly the fibers here jump to compression. There is some problem here, because you cannot simply jump without having an external force that caused the jump. There are apparently ghost external forces being applied on this line, which is of course not the case. If you think this is weird and bad, it gets even worse. So to make it even worse, I want to talk about the displacements. You see, U3 and U4 are not equal, and V3 and V4 are unacceptable. Allow me to explain why I'm supposed to have U3, U4 the same, and V3, V4 somehow related. The reason behind this goes back to the mechanics of materials. In mechanics of materials, you have studied this as a simple rod, as a simple axial element. Let's talk about the right side here, this side. For a simple rod or simple element, your delta equals PL over AE. This is a well-known fact in the mechanics of material course. Applying the loads there, you will get this sort of displacement, which is nice and dandy. Of course, if the bar would elongate, and this is simplification, by the way, the bar would elongate the same everywhere, and the bar would become thinner due to Poisson's ratio. You studied that in Poisson's ratio. If you have a longitudinal extension, the bar gets thinner, and if you have a longitudinal compression, the bar gets thicker. I usually like to call Poisson's ratio the football theory. Why am I calling it the football theory? Well, you see, if you have a football like this and you compress its sides, Poisson's ratio or Poisson's theory basically tells you that it's going to bulge on the other sides and vice versa. So I usually like to call Poisson's ratio or Poisson's theory the football theory, which is totally fine. If you are pulling or basically applying tensile stresses on a bar, it should get thinner at the edges, and this edge should move the same. Well, now it doesn't, does it? No, it doesn't. It does not, because, simply said, BSc level, because of the weakness of the CST element. MSc and PhD level, it doesn't, because it is mesh dependent. Your mesh was not symmetric. MSc and PhD level talk, if you want to have the two bars, 2 points move the same, you would have to discretize like this. This discretization has a chance of giving you node 3 moving the same as node 4, something expected. But in this configuration, the mesh is not symmetric, and because CST is a very weak element, it's highly mesh dependent, and that's the reason why this and this are not equal. Now the strange thing is, the book Daryl and Logan actually celebrates those results. It celebrates those results because 609 is close to 670, error 10%, and 636 is close to 670, error 1%. I don't celebrate those. Why don't I celebrate those? Because I'm frank and I'm a perfectionist. You see, I like to visualize those displacements. So allow me to take node 3 and move it in the x 609 and the y 4.2, which means it ends up here in the x 600 something and the y 4. Take u4, move 660 and 104. The bar is bending upwards, although no force is making it bend upwards. What gives? Well, why is it bending upwards although the force is horizontal? BSc talk, it's the weakness of the CST element. MSc and PhD talk, because of the discrepancy between the stiffness here and the stiffness here. Look, this element is weak in the y direction. This element number 2 at node 4 is weaker in the y direction than element number 1 at node number 3 because this has a larger dimension than this. So there are some problems, as you can see. Not only this, you know what is even worse? Not only is there a problem that those two things are not equal or that this thing is somehow buckling up, no. It's even worse because V3 is going positive and V4 is going positive. Like what gives? I was thinking, according to Poisson's ratio, that V4, yes, V4 should go upwards a little bit, but V3 should go downwards to mimic the narrowing of the element. Because of Poisson's ratio, right? You have tension. So the element should get narrower here and should get narrower here. This doesn't happen, and this is, I don't know, like this is strange. And basically this ends my example for you today. The verdict here I have is that the CST elements are easy to use, easy to understand, but CSTs are not that accurate. And that's everything I wanted to talk about today, and I hope that you enjoyed the video. But before I finish, I want to give a symmetrically discretized sized shout out to our dear channel members in the contributor level and the helper level, whose names are going to be shown on the screen. I want to thank them from the bottom of my heart, as the support of the channel is priceless to me and enables me to provide you with the videos on time, hopefully, and with a certain quality that I try to achieve. With that being said, I hope that you enjoyed the video and that you found it beneficial. Of course, if you have enjoyed the video, then please consider providing a sacrifice to the YouTube algorithm overlords by hitting that like button, subscribing, sharing, and especially subscribing, because it helps increase the reach of my channel. Recently, I noticed we have reached the 2.5k subscribers. This is a milestone and I want to thank you from the bottom of my heart. With that being said, and as per usual, this is the Civil Engineering Essentials channel, and we'll catch you in the next video. Bye-bye.